welcome to the Explainer. So you've probably gotten the hang of basic Python classes. Well, today we're going to level up. We're moving beyond the basics to explore 4 really powerful concepts that will make your code more robust, way more flexible, and, truly Pythonic. First, we'll make our objects act just like functions. Then, we'll figure out how to hide and protect their data. After that, we'll dive into creating these strict blueprints for other classes. And then we'll get into Python's whole philosophy of if it quacks like a duck. And finally, we'll see how to package it all up so you can use it again and again. All right, let's get into it. So, first up, let's just completely challenge a common idea you might have about objects. We're all used to calling methods on an object, right? Like object.doSomething function. But what if we could call the object itself? Well, this secret sauce here is a special Dunder method, _call. Now, we all know _init. It's the constructor. It runs just one time when an object is born. But _call, this is where the magic happens. It runs any time you treat an instance of your object like a function by putting parentheses after it. It basically lets your object lead a double life. And this lets us create something super useful, a stateful function. It's this cool hybrid thing that has the logic of a function, but the memory of an object. It remembers what happened last time. Let's make this real. We'll use a classic example, a class that keeps a running average of numbers. Okay, check this out. Inside our cumulative average class, Dunder init kicks things off by creating an empty list. That list is going to be our object's memory. Then you see our star player, Dunder call. It takes a new value, adds it to that internal list, and then returns the new updated average. Simple, right? So we make an instance. We'll call it av. At this very moment, the constructor has done its job. Our av object is just sitting there holding an empty list, waiting for us to give it some numbers. And boom, here it is in action. Look closely. We're not doing avg.calculate or anything like that. We are calling av itself directly. The first call adds 12 and gives us the average. The second time, it remembers that 12 is already in there, adds 13, and gives us the new average. It's a function with a memory. So cool. Now, having that internal list is great, but it kind of brings up a new question. How do we stop someone from accidentally messing with that data from outside the object? Well, in Python, it's all about conventions and signals. A normal variable name is public, fair game for anyone. A single underscore at the front is a hint. It's like saying, hey, this is for internal use. You probably shouldn't touch it. It's a gentleman's agreement. But a double underscore? That's Python's way of putting up a keep out sign. It's a simple analogy, but it really works. Your bank account PIN? That's private. You don't want anything or anyone messing with it directly. But your name? That's public data. It's totally fine for everyone to know it. And this is where Python actually gets strict. Look, we've got a class with a private variable, double underscore secret. When we make an object from it and then try to grab that secret from the outside, Python slams the door shut. It raises an attribute error. It's actively protecting that data for you. Okay, so we can protect data inside an object. But what if we want to enforce rules on other people? How do we force other developers to follow a very specific design when they build on top of our code? For that, we turn to abstract classes. You should think of them like a contract or maybe a blueprint for a building. They lay down the law for any other classes that want to be part of the family. Let's just walk through a really quick 4-step example and see how this contract enforcement actually plays out. First things first, we create the blueprint. We import a couple of things from the ABC module. Then we make our animal class, but we have it inherit from ABC to signal that it's abstract. Now the key part is that @abstract method decorator. By putting that on the eat method, we're making a promise. We're saying, hey, any class that calls itself an animal must have its own eat method. And this right here proves the whole point. If you try to make an object directly from that animal blueprint, Python literally won't let you. It throws a type error. You can't just have a generic animal, you need a specific kind of animal. So what do? We create a cat class that inherits from animal. And the crucial part is we give it a real, concrete eat method. The cat class has now officially held up its end of the bargain. The contract is fulfilled. And because our cat class played by the rules that the animal blueprint laid out, everything just works. We can now create a cat instance without any problems. This idea of contracts and rules leads us perfectly into one of Python's most famous and maybe most important features, its super flexible approach to types. You've probably heard this saying before, and honestly, it's the absolute core philosophy of what we call duck typing. See, in Python, what an object is named, or what class it comes from, isn't always the most important thing. What matters is what it can do. Here, Python looks at this and sees two different classes, a duck and a person, but they both have a quack method. To Python, that shared behavior is what's really interesting. And this is where it all clicks. Look at that in the forest function. It doesn't ask, are you a duck? It only asks one question. Can you dot quack? And since both our duck and our person object can do that, the function is perfectly happy to work with either of them. It cares about behavior, not labels. And that philosophy is what makes so much Python code so flexible. So, finally, let's say we've designed these amazing classes. They're callable, they're protected, they follow all the rules. How do we actually organize them so we can share them and reuse them? Well, that's what modules and packages are for. And it's really simple. A module is just a single Python file. A package is just a folder full of those files. That's it. It's how you build organized, reusable libraries for yourself or for the whole world. So let's just recap real quick. We've looked at 4 tools to make our code better: callable objects that act like functions with a memory, encapsulation to protect our data, abstract classes to enforce design rules, and duck typing to give us maximum flexibility by focusing on behavior. These are real-world tools you can start using right away. And that leaves us with one final thought. You often hear that Python's philosophy is, we're all consenting adults here. So how does that idea of trusting the developers shape everything we just talked about? From private variables that aren't really private to a type system that cares way more about what an object does than what it is. Something to think about.